Okay. Consider a system like this. Assume this is a rod. Okay, the horizontal one that you see is a rod of mass m, length L, and there are two blocks connected to it. One block's mass is m, the other block's mass is 2m. They are connected by light inextensible strings. The rod has mass, the strings don't have mass. Okay. If we release this system, can any of you tell me what is going to happen?
There it will tilt towards the right.
The right side is heavier, so definitely that side is going to go down. The other side will rise up. So you know it starts rotating. Fine. Calculate the angular acceleration immediately after the rod is released. So you just have to indicate all the forces that act on the system. Then write tau net is equal to I alpha. Okay, and maybe you'll have to use a constraint relation as well. Do this, all of you. Rishi, Aishwarya, any answers? Okay, see, this system is not going to continue to be in equilibrium. Okay, once we release it, we know it will tilt. So we just have to write Newton's second law. Alpha is angular acceleration. No? We just have to write Newton's second law in rotation for the rod. One of you tell me what all forces act on the rod? What are the forces acting on the rod?
So mg its own like weight,
Okay, its own weight. Where does its own weight act?
center of mass,
Okay, it acts
like
everywhere.
center.
We show it acting through the center of gravity, which is same as center of mass. Okay, and what other forces act on the rod?
Tension on both of the strings.
Okay, do you think those tensions will be equal?
There it can vary.
Will the rod rotate or not?
It will rotate, sir.
Okay, if you are sure that it rotates, then you can be sure that the tensions are different, because had the tensions been equal, clockwise torque created by one tension would become equal to the anti-clockwise torque created by the other tension, and the rod would not have rotated, isn't it?
Yes, sir.
But we know for sure it will rotate, so the tensions are unequal. Can you tell me which tension is greater, T1 or T2? Whose torque dominates?
E2.
T2. Okay, so the tension T2 will be greater. Fine. And any other forces acting on the rod? The force exerted by the support. Because if these three were the only forces acting on the rod, it would fall down. Okay, there will be a force exerted by the support as well. We don't know how much it is, and we don't need to know also. If required, we can find out. Okay, but as of now, we don't need. Fine. So one of you tell me which forces can create torque about the point where the rod is pivoted. We have visualized the forces acting on the rod. Which of these forces can create torque about the pivot?
T2.
T2, only T2.
No, mg will also be
See,
be all. It'll also
Rishi,
be
tell
one
me,
of the forces.
how do you decide if a force creates torque about a point or not? Anyone? How do we decide if a force creates a torque about a point or axis or not?
Sir, if it causes rotation.
If the line of action passes through the axis or the point, then that force cannot create a torque. Okay. Now T2's line of action does not pass through the axis. T1's line of action also does not pass through the axis of rotation, so they can both create torques, not just T2. Mg and the force exerted by the support, their lines of action pass through the axis, so they cannot produce a torque. Fine. Now, if you see, we just have to write net torque equal to I alpha on the rod. Then the net torque in this case will be torque produced by T2 minus torque produced by T1. Okay, fine. Aishwarya, you only tell me, how will you express the torque produced by T2? Torque is force multiplied with the perpendicular distance from axis to the line of action of the force. So based on that, you tell.
So L/2 into T2.
T2 multiplied with the perpendicular distance between axis and its line of action is L/2. Okay, that's the torque produced by T2 minus the torque produced by T1 will be T1 multiplied with L/2. That's the net torque. Okay, so T2 minus T1 times L/2 is equal to I alpha. Okay, now when applying tau is equal to I alpha or tau net is equal to I alpha, I told you need to be very careful about whichever axis you are calculating the torque. About the same axis, you must take the moment of inertia. Now, this is the axis about which the torque was calculated. Can one of you quickly tell me what the moment of inertia of a rod is about this axis? Axis passing through its center perpendicular to the rod. How much is its moment of inertia about this axis?
ml square by 12.
ml square by 12, correct. So you can write this as ml square by 12 multiplied with alpha. Okay. But to calculate alpha from this, we need to know T1 and T2, which are not given in the problem. So Rishi, can you suggest any other equations which will involve T1 and T2? We need some more equations having T1 or T2 or both in them.
Sir, constraint equation, can we try
Constant
getting?
equation will never have force in it. No. Constraint relation will just be a relation between the displacements or velocities or accelerations. Force will not be involved in it. Okay. See, last class also we solved some problems based on this. So basically, as this system moves, the disk rotates, the pulley rotates, but the blocks execute translational motion. So we write F net equal to MA for the blocks and tau net equal to I alpha for the disk. Okay, in all the questions that we discussed in last class, that is what we did. Okay, the second and third questions, that is what we did. So for objects that undergo translation, we'll have to write F net equal to MA. Okay, otherwise we won't have enough equations to solve this problem. Fine. So you can see that on 2M, there is a tension T2 acting upwards, and on M, there is a tension T1 acting upwards. T1. Okay. Let's assume 2M goes down with an acceleration A2 and M goes up with an acceleration A1. See, there are a lot of assumptions involved here, and you can't directly take both blocks to be having the same acceleration. Okay, you need to check that. That becomes a constraint equation here. Okay, so for now, we'll consider their accelerations to be different. Can any of you comment on this? Should the blocks have the same acceleration the moment the rod is released? Should both the blocks have the same acceleration when the rod is released? So basically, how to think? You must see how they are related to each other or how they are connected to each other. Now both the blocks are connected to the rod. Okay, that is the common thing between these blocks. Okay. Now one block is at one end of the rod, the other block is at the other end of the rod, and the rod is hinged exactly at the center. So if this rod rotates, okay, we know it will rotate clockwise. If the rod rotates clockwise, call these ends as A and B. A will move up, B will move down. Okay, because the rod is horizontal, at this moment, if the rod starts moving, A is going to move vertically upward, B is going to move vertically downward. At some other instant, A's direction of motion will change. Okay, at the very next instant, A's direction of motion will change. B's direction of motion also will change. But at this instant, when it just starts moving, A moves vertically upward, B moves vertically downward. And since they are both at the same distance from the axis, okay, A's acceleration in the upward direction will be R alpha. Like A is going to execute circular motion. No, every point of the rod is going to execute circular motion except the center. So A's acceleration upward will be L by 2 into alpha. B's acceleration downward will also be L by 2 into alpha. Why? Because they are both at a distance L by 2 from the center or the axis. Okay, and what is this L by 2 into alpha? R alpha, tangential acceleration. They have to be equal. Therefore, the acceleration of m1 in the upward direction has to be equal to the acceleration of 2m, okay, in the downward direction. That way, you have to confirm whether the accelerations are going to be equal or not. Had this second block been connected somewhere here, okay, you'll have a question like this in the next worksheet. So this is the hint for that question. Had the second block been connected here somewhere randomly, okay, then you cannot assume their accelerations to be equal, because if one of them is at a distance L by 2, then that block's acceleration will be L by 2 into alpha in the upward direction. The other block, you need to know where it is connected. Suppose it is connected at L by 3, then its downward acceleration will be L by 3 into alpha. They won't be the same. Okay, you'll have such questions in the worksheet, solve them later. For now, in this system, their accelerations are equal. Okay. Now, what is our aim? Our aim is to derive angular acceleration of the rod, for which we wrote the torque equation, which had three unknowns, T1, T2, and alpha. So we need more equations to solve. So what we are going to do is write Newton's second law for the blocks. Yusuf, can you tell me Newton's second law equation for the block of mass m? It is accelerating in the upward direction. You consider all forces acting on it and tell me how much is the net force. We'll equate it to mass into acceleration. I mean, how to express the net force?
The T1 minus the A.
How can you subtract acceleration from a force? T1 is the upward force. What is the downward force acting on the block?
So G no, so gravity.
mg should be equal to mass multiplied with its acceleration. Correct. Rishi, quickly tell me how you'll apply Newton's second law to the other block.
Sir, T2 minus.
It is accelerating downward.
Yeah, so 2m minus
2mg, okay?
Yeah, minus T2 is equal to 2ma.
2ma, correct. Fine. We got two more equations involving T1 and T2, but we introduced another unknown here, acceleration A. So as of now, we have three equations which have four unknowns. T1, T2, alpha, and A. So we need one more relation. Vanilla, can you tell the last equation that we are going to write? Aishwarya? Okay. The last equation is the relation between the block's motion and the rod's motion. Okay. Linear acceleration A of the rod, of the block will be connected to angular acceleration alpha of the rod. And how are A and alpha connected? A is equal to R alpha, because the acceleration of the block at this moment is nothing but the acceleration of the ends of the rod. And ends of the rod, they are about to execute circular motion. They'll have tangential acceleration R alpha. So L by 2 into alpha. Therefore, the last equation in this problem, or to help you solve this problem, is A is equal to L by 2 alpha. So now you have 4 equations, T1, T2, A and alpha. You can solve for all of them. Okay, I'll leave this here. You solve it later and send me the solution. Okay, so it's it's like those common balance systems. Okay, in a common balance, what happens? That physical balance that will be there. There is a central rod. Okay, at the ends of which 2 pans are connected. In the 2 pans, you put weights. If the weights are equal, the rod will remain horizontal. Otherwise, it will tilt. Okay, it's like that. Okay. So in tomorrow's worksheet, you will have problems based on application of tau net is equal to I alpha. Solve all of them. You go through what we discussed in class. Based on that only you solve. Fine. So before we started talking about torque, we discussed this quantity called angular momentum. We discussed how to derive, not just how to derive. We first discussed what is its meaning. Okay. Basically, angular momentum tells you how difficult it is to stop the rotation of a system. Greater the angular momentum, more difficult it is to stop it from rotating. Then we discussed how it can be calculated for a particle and for a system. And for a system, we discussed how to calculate it in translation, how to calculate it in pure rotation also. Can any of you tell me the formula for calculation of angular momentum of a rigid body in translation? Angular momentum of a rigid. Can you repeat?
M into R bar plus V bar.
R and V, what do they mean? M is the mass of the system. Okay. What are R and V? Anyone else? How to calculate the angular momentum of a rigid body in translation? It is M RCM cross VCM. You treat the rigid body as a single particle placed at its center of mass. Okay, where had we discussed that? This is torque. Yeah. So in pure translation, it is M RCM cross VCM. And in pure rotation, it is I omega, where I is the moment of inertia about the axis of rotation, and L is the angular momentum about that axis itself, axis of rotation. This is also a vector quantity. Whatever is the sense of omega, same will be the sense of angular momentum, or whatever is the direction of omega, same will be the direction of angular momentum. Okay. Fine. One of you tell me, what is Newton's second law for translation?
So F equal to dp by dt.
F net equal to dp by dt. Correct. And if the net force on a system is 0, what can we say? Or what does it lead to?
The momentum is conserved.
Okay. All questions, Vanilla is only answering. Okay, fine. If net force is 0, it means dp by dt is 0. That means momentum is conserved. Okay, we applied this in many situations, block and block collisions, explosions. Okay, and in all different kinds of collisions, we applied momentum conservation. It's one of the fundamental laws in physics, fundamental laws of nature, you can say. Conservation of linear momentum. Okay. Similarly, we have something called law of conservation of angular momentum. Okay. We know that net torque acting on a system about a given axis is the rate of change of its angular momentum about that axis. Okay. Therefore, if net torque is 0, we can say that rate of change of angular momentum is 0. And what does that mean? Rate of change of anything is 0 means angular momentum is conserved, means that quantity is conserved. Okay. So basically, if one object disturbs the rotational state of another object, you can try to apply this principle. Okay, where did we apply linear momentum conservation? Gun firing a bullet, block going and colliding with another block, such cases. Person walking on a boat. Motion of one part of the system disturbs motion of another part of the system. In such cases, we tend to apply momentum conservation. Same thing in rotation you do. It is called angular momentum conservation. Okay, and how do we apply this? First, we analyze the system. We consider what all torques act on it. Okay, and we try to identify an axis. We try to identify an axis about which the net torque is 0. Once you identify such an axis, you can write initial angular momentum about that axis is equal to final angular momentum. Okay, initial and final could be before and after a collision or some process. Okay, some event. So this is what is law of conservation of angular momentum. This is also one of the fundamental laws of physics. There are 4 fundamental laws in physics, or laws of nature, you can say. Law of conservation of energy. Okay, overall energy. Fine. Then law of conservation of linear momentum. Third is this law of conservation of angular momentum. The next one is law of conservation of charge, which we'll use in 12th class topics, not now. So it's very important to understand how to apply this. Okay. Let's consider one situation. Okay, just a moment. Okay, tell me, we'll solve the problem later. Tell me one thing. Do any of you know anything interesting about a cat falling?
So they land on their feet.
They always land on their feet, irrespective of how you release the cat. Okay, they somehow manage to land on their feet. Okay, and that is true. How does the cat manage to do that? Like, it's falling through air. It doesn't have any support or anything. How does the cat manage to adjust its orientation during the fall? Any idea, anyone? Of course, see, the topic that we are discussing is angular momentum conservation. So the answer will be angular momentum conservation. But how is it able to do that?
The angular momentum is conserved.
That correct. That is correct only. How exactly is the cat applying that? Okay, this is another example given in your textbook. A diver jumping from a springboard. If you have ever seen diving, then you will know better that divers, what they are supposed to do is they are supposed to spin mid-air, but finally, just before they land on water, they are supposed to make themselves straight like this, okay, such that they don't create a splash when they land on water. Okay, so in between they are supposed to spin, but finally they should stop spinning, or they should reduce their rate of rotation, angular velocity. But when the diver is in air, once the diver jumps off, they are not in contact with anything. Of course, they are in contact with air, but air is not of much help. They're not in contact with anything else. Then how does the diver mid-air manage to adjust his or her angular velocity? Okay, we'll discuss the answers to these a little while later. Okay, but these are situations where angular momentum conservation is applied. Okay, a cat of course, doesn't know physics, but it applies physics. Right? It's a reflex for the cat. Right? Now we know angular momentum in pure rotation. Angular momentum is I omega. Fine. So for a particular system whose, what do you say? For a particular system on which the net torque is 0, you can say L initial is equal to L final. So you can say I1 omega 1 is equal to I2 omega 2. Okay, I1 omega 1 is its initial angular momentum, I2 omega 2 is its final angular momentum. Okay, in pure rotation, this is how we'll apply angular momentum conservation. Now, there's another example also, just a moment. Fine, the other example, actually, if you visualize only, if you have seen only, you'll be able to understand. Let it be, leave it. So basically what happens, consider the diver example. When the diver jumps off, they jump off with a small angular velocity. Okay, obviously, when you just take off from a springboard or a surface, you can't be spinning very fast. Okay, but mid-air they increase their angular velocity, again they decrease their angular velocity. Now you observe what the diver is doing. Initially the diver is straight. Okay, but mid-air, observe what happens. The diver becomes curved. Fine. So basically what the diver is doing, when the diver jumps off, okay, the diver initially, let's say the angular velocity is omega 1. Fine. And imagine an axis passing through the center of mass of the diver somewhere here. Initially the diver is straight. That means the mass is at a large distance from the axis of rotation. When the diver bends and brings their arms and legs close, okay, as you can see in the 4th and 5th diagrams, okay, basically what happens is the center of mass will be somewhere here. I'll mark it in black itself. The center of mass will be somewhere here, and you can see that the mass is very close to the axis now, axis of rotation. Okay. Even in the next diagram, the diver's body mass is quite close to the axis of rotation. In the first diagram, if you see, from the axis passing through center of mass, the mass is at a large distance. Later, during the dive, the diver brings the mass close to the axis. If mass comes close to the axis, what happens? Moment of inertia decreases. Okay. And if moment of inertia decreases, see I1 omega 1 is equal to I2 omega 2. If moment of inertia is decreasing, then angular velocity will have to increase. Okay. So mid-air, when the diver pulls their or brings their legs and hands together, or what do you say, entire body together, okay, as close as possible, the rate of rotation increases. Okay. So here the angular velocity will be much higher. Initial omega is low. Fine. Now, how is angular momentum conservation getting applied here? Once the diver jumps off, the only significant force acting on the diver is the weight. Okay, weight acts through center of gravity. Now here, the axis of rotation itself is passing through the center of gravity. Therefore, weight does not create any torque. So once the diver jumps off from the springboard, the net torque on the diver becomes 0. And if net torque is 0, angular momentum is conserved. If the diver brings his body close to the axis, his or her body close to the axis, the rate of rotation will increase. If the diver takes their body away from the axis, okay, or takes their mass away from the axis, rate of rotation will decrease. Okay, that is what happens there. Is this clear to all of you, why the rate of rotation or the angular velocity of the diver increases and again decreases?
Yes, sir.
Yusuf, did you understand?
Yes, sir.
Okay, basically it's an application of conservation of angular momentum. Okay, weight of the person does not create a torque about an axis passing through the center of gravity. And there are no other significant forces acting. Air resistance will be acting, but that is negligible. Okay, so net torque is 0. So when the body mass comes close to the axis, angular velocity increases. When body mass goes away from the axis, angular velocity decreases. Okay. Now, how is the cat able to adjust its orientation mid-air. Suppose the cat has fallen off like this. Okay. Now, you take the example of a gun firing a bullet. Okay. Gun firing a bullet happens due to internal forces. There could be a spring inside or an explosion may happen inside, but it is an internal force which fires the bullet. The force which fires the bullet forward also pushes the gun in the backward direction. So initially, the total velocity of the gun bullet system is considered 0. And when one gets positive velocity, the other gets negative velocity. Linear momentum conservation. Same thing happens with the cat's body also. When the cat just falls off, its omega is 0. It's not rotating. So let's say it's just falling. Okay, it didn't start rotating yet. Omega is 0. That means its angular momentum is 0. Okay, about its center of gravity, the angular momentum is 0. Now what the cat does is, it rotates 1/2 of its body in one orientation. Okay, like you can imagine, okay, the cat's legs were pointing upward. Now the hind legs, the back legs, and the back legs are pointed towards us. So they have rotated this way. Then, okay, it's like the rotation is out of the screen. Then the cat's face will rotate into the screen backward. Okay, so it rotates 1/2 of its body in one sense and the other half in the other sense. And see, 1/2 I'm just telling roughly. I can't say exactly 1/2 will rotate this way, one half will rotate that way, but it's roughly like that. So the other half gets rotated like this. Fine. So 1/2 of the body gets positive angular momentum. The other half of the body gets negative angular momentum. Angular momentum is a vector quantity. Net angular momentum still remains 0. Okay. And some cats manage to do this entirely with this tail. With their tail, they don't have to rotate their body parts at all other than the tail. They rotate tail in one sense, rest of the body rotates in the other sense. That is enough for them to adjust their orientation. Okay, so it's like that gun and bullet situation itself. If one mass goes in one direction, the other mass goes in the other direction. One mass gets positive linear momentum, the other mass gets negative linear momentum. Same thing happens with the cat. One part of its body gets positive angular momentum, the other part gets negative angular momentum. So it will somehow manage to get its feet downwards before landing. Okay, it will happen as a reflex. Okay, it will do it almost instantaneously. Is this clear to all of you how a cat applies angular momentum conservation?
Yes.
They're also same situation. The force acting on the cat while it is falling is gravity. Gravity cannot create a torque about its center of gravity. Okay, so net torque is 0, angular momentum is conserved. Fine. Let's consider a situation like this now. Suppose there is a rotating disk. Okay, you are looking at it from an angle, obviously. Assume the disk's mass is m, radius is r, and it is rotating about a fixed axis, which is vertical. Okay, the disk is in the horizontal plane, parallel to the ground. The axis of rotation is vertical. Like this, it is restricted to rotate around this axis somehow. Assume there is an insect on the disk somewhere here. Okay, there's an insect on the disk. Assume the insect mass is m/2 and it is initially at a distance r/3, 1/3 of the radius from the axis. Initially, it is at that distance, and this disk plus insect system is rotating with an angular velocity omega naught initially. Fine. Somehow it was set into rotation and the insect is rotating along with the disk. Now, if the insect starts walking outwards, okay, towards the edge of the disk, what will happen to the rotation of the disk? Can any of you tell? What will happen to the angular velocity of the disk if the insect starts walking outwards?
It will decrease, sir.
Okay, Vanilla is saying it will decrease. Others, any answers?
Can you repeat your question once?
If the insect moves away from the axis towards the edge of the disk, what happens to the rotation of the disk? Will it rotate faster, slower, or it won't get affected? It won't be affected at all.
Sir, it'll rotate slower.
Why?
Sir, because the mass distribution is changing, so it'll affect
Good.
it.
Good. I appreciate you talking about mass distribution. That is very good. Mass is going away from the axis. Mass of the system is going away from the axis. What system? Disk plus insect system. Its mass is going away from the axis. So moment of inertia increases. Angular velocity should decrease. Okay. So let's say in some time, the insect reaches the edge of the disk. Edge of the disk means it will be at a distance r from the axis of rotation. At that instant, you have to calculate its angular velocity. Initial angular velocity is omega naught. In terms of omega naught, how much is the final angular velocity? Okay. So basically, this is a situation where the motion of one object, the insect, disturbs the rotational motion of another object, the disk. Okay. And in such situations, you will see or you will check if angular momentum conservation can be applied. Okay. Remember this always. Motion of one object disturbing the motion of another object, you will try to apply linear momentum or angular momentum conservation principles. Okay. One of you quickly tell me, when is angular momentum conserved? When is angular momentum conserved? Vanilla, don't answer.
Sir, when there's no torque applied to the system.
When the net torque is 0 about a particular axis, angular momentum will be conserved about that axis. Okay. So as I said, the first thing we have to do is identify an axis about which net torque is 0. If possible, we have to identify an axis like that. Now, to identify an axis about which net torque is 0, we first need to consider the forces acting on the system. Yusuf, tell me what forces act on the disk? No response. Anyone else? What forces act on the disk?
Sir, mass and
Mass is not a force. Weight. Okay. Weight and
and
okay, your voice is breaking. See, weight of the disk is one of the forces that will act, and weight of the disk acts vertically downward like this. Okay. That is mass of the disk multiplied with g. Okay. It acts along the axis itself. What other forces act on the disk? Aishwarya? Okay, anyone? What other forces act on the disk?
sir, normal force by the end.
Normal force exerted by the insect that will act downwards like this. And of course, the same normal force will act on the insect like this, vertically upward. Okay. Next, any other forces on the disk? Fine. The pivot or whatever it is, the axis may be supporting the disk from falling down. It can exert its own force, but it passes through the axis anyway. Okay. What forces act on the insect? One of the forces is normal force, which you have already shown. What other forces act on the insect? Anyone? Only other force that can act on it is its own weight.
Gravitational, sir.
Gravitational force, yes. So the own weight of the insect also will be acting, and insect's own weight acts vertically downward like this. m/2 into g. Fine. Now you can see the lines of action of all these forces. They're all vertical, and the axis is also vertical. Rishi, tell me, which of these forces, okay, weight of the disk, weight of the insect, normal forces, which of them can produce a torque about the given axis? Pawan?
Normal force.
Why are you saying normal force can produce a torque about the given axis? How did you decide that normal force produces a torque?
Sir, axis నుంచి perpendicular గా ఉండే force అంటే
That force is perpendicular to what? Both normal force are perpendicular and mg/2 is also along the same orientation. Then that should also be producing a torque.
Sir, అంటే axis మీద mg మ్యాప్ చేయదు కదా.
No, mg/2, the insect's weight I'm saying. Insect
Okay.
is not on the axis, no? But still, why are you saying they'll produce a torque? Means they are at some distance from the axis, that's why they'll produce a torque. Is that what you're saying?
Yes, sir.
Okay. Do any of you want to comment on this? Is what he said correct or not? Can the normal forces...
The normal force is...
Vanilla, continue.
So the normal force is parallel to the axis, so it
Correct.
won't produce it.
Correct. See, forces acting parallel to any axis cannot produce a torque about that axis. We had discussed this before. If the line of action of force cuts the axis, it cannot produce torque. If it is parallel to the axis also, it cannot produce torque. So these normal forces and also mg/2, the weight of the insect, none of them can produce a torque about the own axis of the disk. And the disk's own weight also cannot produce a torque. Therefore, this is the axis about which net torque is 0. And if you can identify an axis about which net torque is 0, you can apply angular momentum conservation to find out final omega values and such. Is the idea clear to all of you? How to find out, or in this case, in this question at least, how we found out an axis about which net torque is 0. Did you all understand or not?
Yes, sir.
Okay. So you could have taken an axis somewhere else also. Okay. For example, the disk is rotating. Okay, let it rotate. Along with that, the insect also will be rotating. That's fine. Okay. You can see the forces that act on them. Even if you had taken an axis somewhere here, none of these forces can produce a torque about this axis. So about this axis also, the net torque is 0. But the problem is that we don't know how to express angular momentum about that axis. As of now, we have only learned how to express angular momentum about the axis of rotation of a system. That purple line that I have drawn is not the axis of rotation. It's a random axis about which net torque is 0, but we cannot express angular momentum. Okay, so that problem will be there. So we won't be considering any other axis. We'll only consider the axis passing through the center of the disk. Okay. Fine. Initially, the system is in pure rotation. Now, when the insect is moving, obviously it's not in pure rotation. It's not executing circular motion around the axis. It's that circle's radius is expanding, but finally it will again be in pure rotation. That final angular momentum is what we'll consider. Okay. So we have identified an axis about which the net torque is 0. Then the only thing that is left is application of conservation of angular momentum. Now, whose angular momentum is conserved? Only disk? Okay, actually, you have not mentioned all forces acting between the disk or on the disk and the insect. You missed one force. Can any of you tell what other forces act?
Sir, is it friction?
Yes, there will be friction, because without friction, when the disk is rotating, how will the insect rotate along with it? Sitting on the disk. Okay. Friction provides the centripetal force here. Fine. In fact, if the insect wants to walk outwards, it has to provide force in the outward direction also. It's complicated, but when it is executing pure rotation, friction provides the centripetal force. So there will be friction between the insect and the disc as well. Suppose the insect is stationary. Okay, let's say that at the initial instant, the insect is stationary. Then on the insect, friction will be acting like this towards the center. I'll use a different color, just a moment. On the insect, friction will be acting like this towards the center. And on the disc at that same point, it will be acting away from the center, action-reaction pair. Okay. But friction's line of action passes through the axis, it cannot produce a torque. Therefore, net torque is 0. You can apply conservation of angular momentum. Now, one of you tell me, whose angular momentum is exactly conserved here? Only disc, only insect, or the combination of disc and insect?
The disc and the ant.
Okay, you want to call it as an ant. Let us call it as an ant itself. So disc and ant, you're saying. Why not only the disc? You see the forces acting only on the disc. None of them is producing torque, no? The way I have shown them, none of them is producing torque.
But isn't the ant a part of the system also, sir?
Okay, let it be. But I mean, the whole system's angular momentum may be conserved. But why not only the disc? How can you say that only disc angular momentum is not conserved? Or is that also conserved?
Sir, but the ant won't rotate.
Why it won't rotate? Friction is there. Friction is there, but friction's line of action, like the way I showed it here, friction's line of action is cutting through the axis. Friction is there, it won't produce torque. If this is how it acts. So is it okay to say that angular momentum of only the disc is conserved? The way I have drawn the diagram here, it's perfectly okay to say that angular momentum of the disc is conserved because net torque on it is 0. Angular momentum of the insect is also conserved because net torque on that one is also 0 about this axis. But actually, I told you one point. Okay. Assume it is in pure rotation. Assume the insect is not moving. Then this is the situation. Okay. If the insect is stationary, it will be like this. If the insect is walking outwards, okay, what actually happens is friction's line of action changes slightly. On the insect, it will be like this. And on the disc, it will be like this. Then the line of action of friction does not pass through the axis. It creates a torque. Okay, now why does the line of action of friction have to change? Because see, when you are standing and when you are walking, there's a difference. Now friction has to act. Friction has to help in walking. So how can you expect this same friction to keep acting on the ant even when it is walking? Whatever friction is acting when it is stationary, it should be different from the friction acting when it is walking. Okay. Now, how exactly did I get the direction and all? Not necessary, but there will be some different direction in which friction acts. Because if friction on the insect acts only towards the center, how is it going away from the center? Now, some of you may say, sir, inertia, it will go. An object moving in a circle, if you cut off the centripetal force, it will go straight. So it will go out of the circle. So it can go far from the axis. Still, the insect has to rotate along with the disc. No, it can't slide on the disc. So friction has to continue acting on it even when it walks outwards. Okay. See, usually nobody does this much discussion in this problem. They'll just say apply conservation of angular momentum. I1 omega 1 is equal to I2 omega 2. You'll get the answer. But you should understand in detail. When the insect just stays there at one place, the friction acts towards the center. But when insect walks, the line of action of friction will change. Okay, and it will produce a torque on the insect. It will produce a torque on the disc as well. So only disc angular momentum won't be conserved. Only insect angular momentum also won't be conserved. But since these frictions are an action-reaction pair, whatever torque friction on the ant is creating, an opposite torque will be created by friction on the disc. So net torque due to friction becomes 0. On what? On the disc plus ant system. Okay, not just on one of them. So hope this is clear to all of you. You can now apply conservation of angular momentum to the disc plus ant system. Do this, all of you. The mass of the insect is m/2. It is at a distance r/3 from the axis initially. Finally, it is at a distance r from the axis. So I just want you to apply angular momentum conservation. L initial is equal to L final about that axis. Whose angular momentum is conserved? Disc plus particle. So moment of inertia of the disc plus moment of inertia of the insect or ant, whatever it is, into omega 1 should be equal to final moment of inertia of the disc plus final moment of inertia of the insect, omega 2. Okay, omega 1 is given to you as omega naught. Put it there. Get omega 2 value. You have to find out the initial and final moments of inertia. Then you will have the answer. Try this, all of you. I'll give you 3 minutes. Right. I got one answer as 5 omega by 9. Okay, 5 omega naught by 9. We'll see. Pawan, tell me, how much is the moment of inertia of the disk about the given axis?
Sir, mr square by 2.
Okay. And how much is the moment of inertia of the insect initially about the given axis?
Sir, mr square by 18.
Okay. Insect will be treated as a particle. We'll ignore its dimensions. Its mass is m/2 and it is at a distance r/3. You square it, it becomes r square by 9. So mr square by 18. Correct. So mr square by 2 plus mr square by 18. 1/2 is like 9/18 plus 1/18 effectively becomes 10/18. So the total inertia, initial moment of inertia is 10 mr square by 18. Multiply that with initial angular velocity should be equal to final moment of inertia. Okay. Nothing has changed for the disk. Okay. Its mass is same, its radius is same, it's still uniform. So the final moment of inertia of the disk is still mr square by 2. But the insect, its mass is m/2. Finally, it is at a distance r from the axis. Okay. So its moment of inertia will be m/2 into r square, mr square by 2. So total final moment of inertia is mr square. Multiply with the final angular velocity. That's all. Therefore, final angular velocity becomes 10/18 is 5/9 times initial angular velocity. Pawan, why did you not give the answer then?
Sir, chatting lo ante మీకు పెట్టలేకపోతున్నాను సార్.
You can unmute and tell the answer. Who asked you not to unmute? Okay, maybe I said type your answers in chat. Others, did you understand? Yusuf, is this clear?
Yes, sir. Yes, sir.
Rishi, Aishwarya.
Yes, sir.
Rishi, tell me, where were you stuck? Why did you not give an answer?
Like calculation mistake.
In what? Moment of okay, obviously moment of inertia. Fine, fine. Practice that a little. Okay, let's consider another question. Okay. Again, disk and an insect system itself. This time the insect is, or the body of the insect is aligned parallel to the circumference of the disk, whatever it is. Assume the disk mass is m, radius is r, insect mass again m/2 itself. Its size is negligible compared to the radius of the disk, so you will treat it as a particle. Assume this system is initially at rest. Okay, and the axis that is there is perfectly frictionless. So the disk is free to rotate about the axis. They'll mention that in the problem. Okay, disk is free to rotate. Aishwarya, tell me, if the insect starts walking along the edge of the disk, what happens to the disk? Initially, they were both at rest. If the insect starts walking, what happens to the disk? Rishi, what do you think?
If the insect starts moving,
Walking along the edge of the disk, what happens to the disk?
then it will tilt a bit towards the insect's
See, tilting
side.
is not allowed. Tilting is not allowed. The disk is fixed to rotate about this axis. Okay, the axis is rigid.
So is it all is it already in motion before the
No,
uh,
the disk and insect were at rest initially. Now the insect starts moving. What happens to the disk?
it'll start moving with the insect.
Why? How can the disk go
Like,
along with the insect? I mean, how can the disk rotate along with the insect?
like it won't go along, it'll go opposite of it. Like
Opposite.
if
Okay, correct. The disk rotates in the opposite sense. Fine. Vanilla, tell me, what force makes the disk rotate? What force makes the disk rotate?
The friction because of the ant.
Friction between the disk and the ant. Correct. Okay, wait. Let us replace the disk with this one just to visualize better. Okay, the disk is restricted to rotate about this fixed axis. It has no other choice, and it cannot move away from that axis also. And the insect is somewhere here. Right. Now, if the insect wants to walk along the disk, friction has to come into play. Initially, angular velocity of the disk and angular velocity of the insect were 0. Now the disk wants to walk along the circumference. So the friction has to, when you want to walk, friction is what helps you walk. So friction on the insect has to act tangentially like this. Now, the yellow arrow that I have drawn is the tangential arrow actually. How do I show it in this diagram? It's slightly difficult. It's like this, parallel to the disk. Okay, it's not in the vertical direction like the axis. It's parallel to the disk. And the same friction will act on that point of the disk in the opposite direction. So this friction helps, one friction helps the insect move clockwise. The friction that acts on the disk makes it rotate anti-clockwise. Is it clear to all of you? Did you understand the picture situation? If you have any doubts, you can ask. Okay. So basically, if the disk is in the XY plane, okay, assume this is the Z axis and the disk is in the XY plane, these two frictions are acting in the XY plane itself, parallel to the disk. One is acting on the insect, the other is acting on the disk. And you can see clearly that their lines of action are not passing through the axis. If you look at it from above, Okay, the same situation if you look at it from above. This is what it looks like. This is the axis of rotation of the disk. The insect is here. Insect wants to walk along the tangential direction. So on the insect, friction will be this way, acting this way. So you can see that there is the line of action of friction does not pass through the axis. It's not parallel also. Okay, axis is perpendicular to your screen. In this view, friction is on your screen. Okay, so they're not parallel to each other and they're not cutting each other also. So friction on the insect creates a torque about this axis. But the same amount of friction acts on the disk in the opposite direction. And that creates an opposing torque. Okay, that is what makes the disk rotate in the other sense, opposite sense. So if the insect moves this way, the disk rotates the other way. Fine. Let's solve problems based on this. Initially, the system is at rest. Okay, keep that point in mind. First question. If the insect starts walking with a speed v along the edge of the disk, okay, remember its angular velocity is not given, its linear velocity v is given. Okay, linear speed v is given along the edge of the disk. What will happen? The disk will rotate. Derive angular velocity of the disk. And this v that is given to you is with respect to ground. Okay, so as seen by another observer, the insect moves with a speed v. Then what is the rate of rotation of the disk? Do this all of you. Disk mass is m, radius is r, insect mass is m/2. Initially, the system was at rest. One answer I got is v/r for the disk. Let's see. This is the top view. This is better to visualize actually. But you have to keep the actual view also in, actual situation in mind. Okay. The first thing to do, if you want to decide, if you want to do any calculation, is visualize the forces. On the disk, what forces will act? Its own weight will be acting, and force exerted by the support. Okay, that axis that is there, the disk is fixed to that axis. It cannot fall down. So that will be supporting the disk. But whatever it is, the support will exert a force at this point only. It cannot produce a torque. And the own weight of the disk also cannot produce a torque. Why? Because it acts along that axis. Next, the other forces acting on the disk are the normal force exerted by the insect like this. Normal force exerted by the insect presses the disk in the downward direction. It will be parallel to the axis, it cannot create a torque. And friction between insect and the disk can create a torque because friction's line of action does not pass through the axis, it can produce torque. So angular momentum of only the disk is not conserved because friction produces a torque. Other forces don't produce. Okay, what forces act on the insect? On the insect, there will be a normal force from the disk like this. The insect's own weight will be acting like this, and friction will be acting. The normal force from the disk on the insect is parallel to the axis, no torque. The insect's own weight is parallel to the axis, no torque. But friction on the insect does not pass through the axis, it's not even parallel to the axis, it creates torque. Okay, that is what helps the insect gain that angular momentum. It is moving in a curved path, no? Or it is moving such that its line of action doesn't pass through the axis, so it is gaining angular momentum. Friction's torque is what helps the insect gain angular momentum. Okay, and in which sense is the insect gaining angular momentum? Anti-clockwise. angular momentum of the insect, it is anti-clockwise like this. And angular momentum of the disk will be clockwise like this. Because friction acts in opposite directions, it creates torques also in opposite senses. Fine. So only for insect, angular momentum is not conserved. Only for disk also, it's not conserved. But if you take insect plus disk as one system, then you can see that the lines of action of these frictions are the same. Whatever anti-clockwise torque one friction creates, the same amount of clockwise torque the other friction will create. Net torque is 0. Okay. So you can apply angular momentum conservation for the disk plus insect system. Okay. So total initial angular momentum of disk plus insect should be equal to total final angular momentum of the disk plus insect. Okay. Initially they were both at rest. So total initial angular momentum is 0. Finally, now when you see from above, okay, you can visualize the rotation clearly. One of them rotates anti-clockwise, the other rotates clockwise. Usually, anti-clockwise rotation, if you curl your right hand fingers anti-clockwise, thumb will point in the positive Z direction. So anti-clockwise rotation is considered positive rotation. Clockwise rotation is considered negative rotation. Okay. So insect is moving with a speed v. Okay, but it's moving in the tangential direction. No, it's moving along the edge of the disk, means it is moving tangentially. So the velocity of the insect is this way. The perpendicular distance is the radius. Its mass is m by 2. Therefore, its angular momentum about this axis becomes m by 2 into r into v. R and v are already perpendicular. You don't have to take components. So final angular momentum of the insect is m by 2 rv and positive. So we'll write it as plus, or you can simply write k cap. Next, disk's angular momentum. What you have to find out is the angular velocity of the disk. Let it be omega. So disk is in pure rotation. How do we write angular momentum in pure rotation? I omega. About the given axis, I for the disk is mr square by 2 into omega, and it is anti-clockwise, so minus k cap. Sorry, this is clockwise, so minus k cap. Insect was anti-clockwise, disk is clockwise. That's all. That negative term you send this side. M will get cancelled, 1 r will get cancelled, 2 will get cancelled. You will get omega is equal to v by r. That is the angular velocity with which the disk rotates when the insect walks along the edge of the disk. Is this clear to all of you? First thing to do is to visualize forces along with lines of action. Then check if net torque about the axis is 0 or not. In this case, if you take insect plus disk as one system, the net torque is 0. Then we applied angular momentum conservation. Now in the problem, I highlighted this. Speed is v with respect to ground. Why did I mention that? Because these are the forces acting as seen from ground. What do you mean? If you see from somewhere else, will some additional forces act? Yes. If you take a point on the disk as the reference, the whole disk is rotating, then a point on the disk will also be rotating. Anything which is moving in a circle is accelerated. If you take a point on the disk as the reference, it becomes an accelerated reference frame. What are accelerated reference frames called?
Non-inertial.
Non-inertial frames. And when analyzing from such a frame, what do you apply? What should you apply? You will have to apply pseudo force. Okay. And pseudo force can produce torque. We'll discuss point of application of pseudo force and torque produced by pseudo force in the next class. So it is important to know with respect to what the speed is given. Another way the question can be asked is like in those gun firing bullet cases we discussed, or person walking on a boat case also we discussed. Just a moment. Conservation of linear momentum. Yes. Where are those questions? Okay, maybe next class we discussed. Yes. So if the person starts walking with a speed v, what is the speed of the boat? Okay. Here we discussed two kinds of questions. Speed v with respect to ground and speed relative to boat. the approach will be different. In one case, the actual speed is given. In one case, the relative speed is given. You can't substitute relative speed in momentum equation directly. You have to get the actual speed. Okay. So we had these many lectures after that. Okay. So you can even be asked such questions here. The insect is moving with a speed v with respect to ground is one way of asking the question. Another way of asking the question is insect walks with a speed v relative to the disk or on the disk. That means the actual speed of the insect is not v. Okay. On the disk, it is moving with a speed v, but the disk itself is moving in the opposite direction. Then its actual speed will be less than v. Okay. How to deal with such situations we'll discuss in the next class. So let's quickly go through what all we discussed today. See, these concepts are very, very important. Give some time to revise these ideas first. I'll send you the notes. Last lecture I didn't upload, but last one and this one I'll upload today itself, or most probably by tomorrow morning it'll be done. Go through the lecture once again if necessary and solve the practice problems. Okay. The ones preparing for NEET, you don't have to go into that much detail about what exactly is happening with the forces and all. Roughly remember the ideas at least. Okay. But the ones preparing for JEE, mains or advanced, you must understand everything in depth. Okay. So first we discussed one problem which basically was an application of tau net is equal to I alpha and some constraint equations. Then we talked about angular momentum conservation, which is one of the fundamental laws in nature. Okay, laws of nature, fundamental laws of physics. If the net torque of a system about any axis is 0, angular momentum is conserved about that axis. So if you want to apply this, first, how do you get the idea that this concept is to be applied or this condition is to be checked? Some change must be happening in a system in terms of rotation. If that is happening, you should get the idea that maybe we can apply conservation of angular momentum. Okay. And how do you apply? First, identify an axis about which net torque is 0. How do you do that? It's not as simple as we write here. You first have to visualize forces. As the system moves, you have to visualize what forces act on it, which of them create torque, which don't create torque, which is the axis about which net torque is 0. All that you will have to find out. Then write initial angular momentum is equal to final. Okay. After that, what we saw is all the application of that. Fine. So next class also we will be continuing with this, and tomorrow you will be given a worksheet you have to solve. Next class we'll solve some more problems based on angular momentum conservation. After that, we'll discuss a third type of motion of a system called combined translation and rotation. So far we have discussed how to deal with translating systems and systems which execute pure rotation about a fixed axis, like this disk or ceiling fan, such situations, such systems. So next class we'll also discuss how to deal with systems which execute both translation and rotation. Okay? And how to apply energy conservation there, angular momentum conservation there, how to find out torque and all. So there is still a lot left in this chapter. This is, as I said, this is the biggest chapter in your entire syllabus, and it is the most important also. These concepts will be applied in chapters after this. And I'm telling you, with this chapter, the fundamentals are almost done. Okay, the chapters after this, gravitation, solids, fluids, and all, mostly they involve application of the ideas that we have discussed so far to new systems. Like gravitation means between two masses, like maybe planet and satellite, okay, planet and sun. In that kind of a system, how to apply these ideas. In fluids, you will learn some new forces called buoyant force, surface tension. But again, all these ideas will be applied with those forces. Okay, so fundamental laws that you learn will end with this chapter in mechanics. The rest of mechanics is just application of these laws in new situations. And then towards the end of your 11th class syllabus, you have fluid mechanics. In that, some new ideas will be there. And after that, waves and oscillations. Waves and oscillations are mostly applications of this only in new situations. Okay. Right. We'll continue in the next class. Thank you all.